Hey guys, we're going to learn about the equivalence principle right now. It's pretty cool. We begin by, drawing some elevators. It starts with elevators. And I think we want four of them. And we're going to do like situations and compare, right? So let's start with this. So I'm in an elevator on the Earth and it's not moving, or maybe it's moving at constant velocity. It doesn't matter, right? Let's just say it's not moving and its acceleration, right, is zero. And this is a closed box, meaning, no windows or anything. So if you were to do the Newtonian thing and draw a force diagram, you would get on the person, right? Person of mass m. The whole point of the elevator is that they're in a closed box, but you're just focusing on the forces on the person. So gravity and the normal force, right? And you would say, the normal force equals mg because they're not moving. Great. If, so here's going to be like the through line here. And the whole point is on this part, on the top part here, it's going to be like on Earth. And down here is going to be in space, right? Um, on Earth, we're going to assume that the acceleration of gravity exists and is 9.8 meters per second, right? And in space, we're going to just assume that there is no gravity. I really mean in deep space between galaxies. We've gone over gravities everywhere. Technically, gravity is never zero, but let's just say it's negligible. Great. But our spaceship is accelerating upward at 9.8 meters per second. Ooh. In both of these cases, the general question is going to be, what does the person feel? I'll use the pronoun you. What do you feel? Pretend this is you. I like that because you can, kind of do a meditation right now of beating on the earth. Maybe you're in a room. Pretend you can't see outside. You can close your eyes if you want, and you realize you feel this pressure. Now, your mind might write that there's gravity, but pretend you're in a spaceship, and the spaceship is accelerating upward. Just like when an elevator accelerates upward, you feel heavier, right? In both of these cases, you feel a normal force equal to m times 9.8. Whether you call that g or a is irrelevant. It's 9.8 m, right? You can confirm that pretty quickly with F net equals ma. And if this elevator were to suddenly be on the Earth, but then start accelerating up, say its acceleration upward is 9.8 on the Earth, then we would write F net equals ma. A is G, positive up, right? Negative mg down, the person's force of gravity. And normal force, which we now realize has to be bigger to produce this acceleration. Now, technically, we shouldn't draw this in our free body diagram, our force diagram, because that is information, that's not a force. So information maybe can go over here, right? Acceleration is positive g. And yes, now that does get plugged in there. So F net comes from the diagram, up minus down. Normal force minus mg equals mg. So the normal force is positive 2 mg. Great. If we're in space and this is a closed box, right? What acceleration produces the exact same normal force? Well, I think that's obvious since there's no other force. F n equals, right, 2 mg. So the acceleration is 2g, right? Which means that this is also the same as being on another planet with gravity. You're just standing there in a closed box, and gravity is 2g. Sorry, that's acceleration. Acceleration of gravity is 2g, or I should say it's g, call it g2. Planet 2 is downward. I won't write negative, just we know it's downward at, that's supposed to be an A, by the way, of 19.6. Had to do that math for a second in my head. 19.6 meters per second per second. Sorry, I'm saying 19.6. The point is this is equal to this is equal to this. All feel a normal force equaling to 2 mg, or we should say 19.6 m. This is called the equivalence principle. That if you were in all three of these boxes, could you tell the difference? The answer is no. Sorry for my handwriting, but I think that that makes sense. Could you tell the difference? No. I'm going to say this in words. This is enormously important. If you were in an accelerating upward, an elevator accelerating upward, you couldn't tell the difference between being in an accelerating elevator and if you're suddenly on a planet where the gravity is getting stronger. That's why you feel heavier. This is also why I don't feel that normal force is an accurate definition of weight because it's an illusion. Like if I push on the wall, I guess my hand feels heavier, but that's not the weight of my hand. So to say normal force is weight, I think in so many circumstances doesn't make sense because you're not actually weighing more because the planet didn't actually grow stronger. You're just accelerating up in this case. In this case, there is no planet, so there's no gravity. So like it's an apparent weight. So in all of these, that's why I like that term apparent weight. Your apparent weight is, right, 2 mg in all of these situations. 1, 2, and 3. Ready? Give me a second. I'm gonna write it in big letters. Ooh, what color? Let's do this one. There is no experiment that can show the difference, assuming, of course, you're not looking outside. This is the closed door or a closed room experiment. There's no experiment, so I call it the elevator experiment. There's no windows on an elevator typically. There is no experiment that can show the difference between 1, 2, and 3, meaning an accelerating room, normal force, and a room in a gravitational field. Or I just say like a room on a planet or moon, etc. Isn't that crazy? This is called the equivalence principle. At least this is one way to word the equivalence principle. It's worded, I think, a little more generally. I know a little more generally in a way that I think this actually shows it better. It's basically like, here's what it really means. And I'm trying to remember the purely general way of doing it. And I can't off the top of my head, but that's okay because I just wanted to show this. There's no experiment that can show the difference between you being in a room on a planet. This is a hint. This is hugely a hint. And a room, a rocket, whatever, accelerating at the same uh, speed of the gravitational acceleration on that. A room, accelerating room at A, call it, yeah, just call it A, and a room in a gravitational field where G is A. So I gave the examples of 9.8 on the left, of course. You feel the normal force. I think the most important thing about the equivalence principle is another way to word it is gravity is the only force you don't feel. You feel an electric shock, you feel, I know that's just very human, but I would say any object that can experience anything doesn't feel gravity. In fact, free fall is called, weightlessness. And I know this comes from the concept of normal force being called weight. I would call it apparent weightlessness, just like apparent weight. And that's just me, and most other physicists call it that. Free fall would be like apparent weightlessness. You feel nothing. This is why astronauts appear to float because they're in free fall. An orbit is a free fall. International Space Station here, going really fast, 7.67 kilometers per second. That's pretty fast because there's an enormous amount of gravity that's trying to pull it toward the Earth, and it's just free falling around the Earth, so they appear to float. So this to me reveals the nature of gravity. So if it's the only force, then the last thing I'm going to say is this, and this is going to be something we're going to want to explore. Is it a force at all? What is a force? In the Newtonian world, it's treated as that, but Newton, modeled gravity with this formula. Technically, there's a negative sign in there, which just means attractive. And he did not explain where it came from. This does not tell us the nature of gravity. This is a mathematical model that works to approximate everything from the orbit of planets and moons to, falling apples. So the story goes, but really it's the law of like gravitational bodies, right? And that was really an epiphany to realize that, stars, planets, galaxies, although galaxies weren't known at the time, but in hindsight, all of those things are the same as just dropping an object on the Earth. It's universal. Does not tell the nature of gravity. or the origin. Boom. I'll leave you to not just think about that, but to feel it, to again be present. It's so omnipresent. This isn't some abstract concept. Like this is as much here and now as anything's going to be. So that to me is a profound realization. So go ahead and sit with that. See if you can imagine another model that could create this universal equivalence. And we're going to explore. So look, we're going to call this observation number two. We already did observation number one. Gravity is omnipresent. All masses fall equally. I'll kind of group those into one, right? Now, that can and can't be explained with Newtonian gravity. So we're gonna, this one's a big one. I mean, it's really right here all the time. Like this is the truth of existence. So even if you think you come up with an answer, don't stop there, right? Just like integrate it into the realization of what reality is. It's my invitation. Have a beautiful day.